With the Air Resources Board. I'd like to just start by saying that it's a particular pleasure to be here under the current circumstances where we have Dr. Sawyer from UC Berkeley as chair of the board, and by now you at the Air Board know that our loss at UC Berkeley with Dr. Sawyer moving up here is your gain because he's just a tremendous individual, and we really, he's still a presence at UC Berkeley, but we miss having him around, but we are very proud to have him in such an important role for the state. I also want to say it's a real pleasure to have Dan Sperling on the board now, who's my mentor and dissertation advisor and close personal friend at this point, and mentored some of the other people in the room, I know, so we're all very proud of Dan, and I know he'll be a real asset to the board as well with the immense amount of knowledge that he has gained over his last many years of working in the transportation energy field. Well, today the topic is hydrogen energy stations for co-production of electricity and hydrogen. And I've been studying this for a number of years now, and I've done some analysis in the past, and then I've been doing some new analysis that I'll be sharing with you today. Before we get into that, I wanted to do a few things. One is to mention that we had a greenhouse gas cap and trade conference at UC Berkeley last week. And were any of you aware of this? Because I want to make sure to mention it. It was really quite a successful conference. It was run by the law school at UC Berkeley with other groups collaborating. And we had Senator Dianne Feinstein as the keynote speaker on Friday. And I knew that, that Barbara Boxer was very passionate about greenhouse gases and global warming, of course, because we know that she's going to be one of the point people in the Senate on that. I guess I didn't know that Dianne Feinstein was also as enthusiastic as she is. And she gave a great keynote speech, which I brought a copy of. I think this will be on the website soon, which is, I don't have the exact web address, but it's, if you type Berkeley greenhouse gas cap and trade or something like that, you'll get to the website for that conference, and I think they'll be posting her remarks. And she talked about 4 or 5 different bills that she hopes to help sponsor in the Senate to address greenhouse gases, sort of a sector-by-sector approach. But one of the things she said that it would be of particular interest to the Air Resources Board is that she said that she hoped to make the Pavley Law a nationwide program as one of those bills, which would eliminate the lawsuit that the automakers have brought and basically just undercut it and have that be a nationwide standard. So that's going to be a pretty tall order, I think, to get that accomplished politically, but I thought that would be interesting. I imagine that would have brought any ARB people to their feet with the phos if they had heard that. So I just want to mention that. It was kind of funny because it turned out that Dianne Feinstein, that was the first time she'd ever given a talk at UC Berkeley, she said, which I found kind of surprising because her husband has a very high position with the UC Board of Regents. So it was interesting that she had never done that. Now, she was dressed in a cardinal red, and it turns out that she went to Stanford as an undergraduate and said that she had mixed feelings about giving talks at UC Berkeley. But anyway, it was kind of funny. Dr. Sawyer and I also went to Stanford undergrads, and we've never had a problem giving talks at UC Berkeley. So I don't know what her issue is. Okay. I just what's that? Technical difficulties. Okay, well, no problem. What I want to do, I'll kind of start talking through the outline. What I want to do is, talk about hydrogen energy stations, of course. But before we get to that, I thought I'd spend maybe 10 minutes talking about some of the recent research we've been doing at UC Berkeley, because almost all of the things I've been involved in lately are of interest to the Air Board, I think. And so I was going to show a slide or two on each of the projects that I've been working on lately, and then we'll get into the energy station part of the show. A little bit of a technical glitch. So I'll just start talking about one of the projects. One of the things we've been doing is testing the Daimler Chrysler F-Cell vehicle. There are about 25 of these in the state of California right now. And we've had the F-Cell for about 15 months and have put, okay, great. It's much better when I can show visuals. So here's the outline again. I'll talk a little bit about research projects, then an overview of the energy station concept for those who are somewhat new to it. Some recent analysis results I'll start with, which are some cases I'm doing right now that are using better assumptions than I used when I did this analysis 4 or 5 years ago. And then I'll go through some previous results because they're a little bit more expansive and show some interesting insights, I think, and the things that I'll be redoing. I'll touch on the idea of high-temperature fuel cell-based energy stations. Mostly I'll be talking about low-temperature based stations, but there's some really interesting concept of using a high-temperature fuel cells, molten carbonate fuel cells, solid oxide fuel cells. And Joe Heinzman's in the room here from Fuel Cell Energy, and they have some very interesting technology that could form the basis of high-temperature fuel cell energy stations, and that's something I'm hoping to analyze in detail in the future, and then we'll make some conclusions. Okay. First of all, I thought I would do one thing, which is to harken back to the first research project I did for the Air Resources Board. I'm working with a number of colleagues at UC Davis back in the late 1990s. This is when battery electric vehicles were all the rage as the leading zero-emission vehicle option. And we were tasked by the Air Board to do a cost study of battery electric vehicles. And this was with Mark DeLucchi, Andy Burke, Marshall Miller, Dan Sperling, and I was a lowly graduate student, low guy on the totem pole who got to do a lot of the grunt work, just gathering data and trying to sift through it and develop cost functions for some of the underlying components of electric vehicles. I want to mention this because I've been doing a lot of work on hydrogen in recent years, and I talk about it a lot, and I'm enthusiastic about hydrogen, although I try to be pretty cautious about it because there are a lot of issues left that we can talk about with why hydrogen is still a ways off as a vehicle fuel. And I just wanted to show this because battery electric vehicles, while still suffering important limitations, I think are an option that should still very much be on the table. And if you look, what the numbers I wanted to point to here are these break-even dollar per gallon numbers over here, the lower sets of numbers for two vehicle types, Taurus and Escort, and then these are battery types, and then the second line are driving ranges for each battery type. And I don't want to spend a lot of time on this, but when we did this cost study, this was the late 1990s, gasoline cost about $1.50 a gallon. And so that was a very, high bar, if you will, to try to achieve to get the cost down that low for battery electric cars. And we were forced to conclude, because none of these costs were below, the lowest one is kind of speculative here with a kind of advanced battery that really didn't exist yet, and 100-mile range vehicle, you could get about $1.80 a gallon. So that was kind of our best case. We couldn't really conclude that battery electric vehicles were going to have break-even costs that were similar to gasoline vehicles. We didn't have any preconceived notions going in. We were hoping kind of privately that we might show something a little more optimistic because of how clean battery electric vehicles were. But I'd like to revisit this because, first of all, note these are in year $2,000, so we would have to inflate these a little bit today to today's prices. But look at, some of these prices are really, in the ballpark of today's gasoline prices. And so as gasoline prices have risen in the last several years, battery electric vehicles are looking more competitive on a life cycle basis. And so I really think, it'd be worth taking a new look at this, taking the latest battery information that, some of which we'll be getting from this new report coming out from the ARB and so forth. But I just want to stress, it's not all about hydrogen. I think battery electric vehicles could play an important role, and with today's gasoline prices, they could potentially compete. Oops. A little fast there. First of all, I did want to mention we have a new Transportation Sustainability Research Center at UC Berkeley. It's a joint venture of about a half a dozen campus research groups. Professor Farrell, Alex Farrell, who's pretty well known to you guys at the Air Board at this point, has been named director of that. I'll be serving as a research director and helping to facilitate research projects. And we have various projects underway, including a new working group for alternative transportation fuels, where we're bringing various professors in, try to understand what people's interests are, and develop some new research proposals for large-scale research projects. Okay? Pause just for a second here. Well, here's our little baby. This is the fuel cell car that we've been testing at UC Berkeley. It's a Daimler Chrysler F-Cell that many of you recognize. And we've had it for about 15 months. We're trying to put about 10,000 miles a year on it. That's been a little challenging because the vehicle range is only about 100 miles, as many of you know. So we've had a little bit of difficulty achieving that mileage target, but we've put several thousand miles on it. We've had various people driving it at PATH, but more interestingly, we were running a research project for Daimler Chrysler where we had about 50 people around the state participate in a study where they were surveyed every 3 months about how they liked it compared to their conventional car. The reason we did it that way is that sometimes with a new technology, there's kind of a novelty effect where people really like it at first, but then as they get more experience with it, they start to have more of a realistic impression as their interest or their impressions kind of settle down a little bit. And so we wanted to do this kind of longitudinal study to study that. Now we were restricted by the that's good timing, you guys. We were restricted by the by the contract to release that report right away. There was kind of a cooling off period where we had to produce the report for Daimler Chrysler, let them digest it for a little while. I looked at the contract the other day, and the release date for the report is March 1st. That's tomorrow. So I was like, can I show a few of those slides of the result? Like, well, let's see, it's almost 2 o'clock here in California, so in Detroit, it's almost the close of business. But in Stuttgart, it's like almost 11 o'clock, right? So at this point in Stuttgart, I don't think people are watching a webcast of some guy in California giving a talk on hydrogen energy stations. At least I'd be a little surprised if they weren't out like drinking beer or in bed by now or something. So I'm going to go out on a limb here a little bit. I'll show a few slides, and then I'll hold up a chart of my lawyer's phone number, and if they want to come after me, they can do. Before I show those results, though, I just want to give you a preview of those and tell you where the report will be available. I just want to mention really quickly, too, we've got some money from Caltrans to do some ride and drive clinics this summer. 2 sets of ride and drive clinics with fuel cell vehicles, one in the Bay Area for University of California employees, where we're going to have 100 people come and take a short test drive of a fuel cell car, witness the refueling of the vehicle. They won't be able to actually refuel, but they'll witness the refueling and then fill out a survey on what they think of all of that. And then we'll do another one up here at the Fuel Cell Partnership with California state employees. So if you're interested in that, stay tuned. That'll be this summer. We're having a little trouble getting permission from the university to do that because the university is very risk averse about doing things that involve human subjects, particularly putting them in new hydrogen-powered cars and stuff like that. So we're having to work through that, but I'm sure we'll be able to get permission with a little more work on that. So here's a little bit on that F-cell study. I just want to show this to you really quickly. Again, the report will be available as of tomorrow. If you email me or look on Institute of Transportation Studies website, you should be able to find it. We had the 3-round longitudinal study. We had 65 drivers in the initial pool who completed the first round survey, and then we got 49 people to go all the way through all 3 rounds. There was a little bit of attrition as we went along. We saw generally high acceptance of the vehicle. I mean, people really typically liked it, except with regard to the driving range, which at 100 miles is obviously pretty limited. But I do want to caution you that the sample we had was sort of necessarily self-selected. So this wasn't just a cross-section of humanity that we had driving these vehicles, where you could then take those results and try to generalize them to a larger population. First of all, Daimler Chrysler chose the companies, the organizations that would have the F-cell vehicles, so that's not random. And then within those organizations, certain people were either assigned to drive the vehicles or volunteered to drive them. And then among those people, we had people volunteer for the study. So keep that in mind. But what we found was that on a scale of 1 to 5, and this shows 1 to 4, but with 5 being excellent, we found that in terms of the overall impression of the F-cell vehicle, and this is through the 3 rounds of the survey, the overall acceptance was between good and very good, and even closer to very good, and fairly stable throughout the 3 rounds. We did see it go up a little bit and down a little bit, but fairly stable, high overall impressions. In terms of safety, this is one I think the most interesting results is that people seem to get a better feeling of safety over time as they had more experience with it. They seem to feel safer, and we saw a significant trend there where by the end they agreed that they felt equally safe driving a hydrogen-powered vehicle as a gasoline vehicle. This was sort of an interesting question. We asked people, what do you think is an acceptable range? Because they didn't like the 100-mile range. We thought they would say something like 300 miles because that's what conventional vehicles get. We actually found that they would be, most of them seem like they'd be pretty happy with more like 200 miles for this type of vehicle, which, I think they're thinking more of a commuter vehicle. But if we get to 200 miles, they seem to think that would be pretty good. And I think that is interesting because some of the vehicles are already getting about 150 miles range, and 200 doesn't seem out of the question. So the thought that we have to get all the way to 300 or 400 mile range in a fuel cell vehicle for people to find it acceptable, I'm not sure is true. And I think that may be somewhat encouraging. All right, talk really quickly about another project. This is the EasyConnect project at Pleasant Hill. This is a really fun project. It's this site, the Pleasant Hill BART station, is a site of a future transit village, a $500 million development by Millennium Partners, similar to some other transit villages that have been built in the Bay Area, sort of a mixed-use residential retail operation. And the EasyConnect project is intended to address the last mile problem, where people get off a train, but they don't, it's a couple miles to their office or their meeting, and they don't want to take a cab at that point. So a lot of people just say, heck with it, I'm just going to drive, rather than taking the train. So the idea with this project is that users can select a low-speed vehicle and get off the train and kind of seamlessly take a small electric bike or a Segway scooter, go that last mile to their office, and sort of have a short-term rental of one of these nifty little vehicles. And we're working with the California Stationary Fuel Cell Collaborative, Mike Tolstrup, who's here, to add a component to that where we're going to add some neighborhood electric vehicles that'll be charged in the parking lot with a little clean charging station that's fuel cell powered. So that's the CleanCharge component that's coming soon. So this is what it looks like right now, where we have users who can walk up to these really nifty lockers that were designed by an architect colleague of ours, and they have a neat card key reader system, so you can put a card in that then bills you for the time that you've taken one of these devices. Right now it's limited to a select group of users that work at a specific office space as a test, but we're hoping to have it kind of move into more of a commercial venture with a new guy coming in who's going to take it over and try to make a business out of it and make it available to a wider group of users who could reserve it on the internet and then do this. So we're pretty excited about this. This is what the CleanCharge component will look like. Will be a fuel cell supplied by Altergy Systems of Folsom, California, so California fuel cell manufacturer. There'll be 6 K bottles of hydrogen. We looked at some other hydrogen supply options, but this is the one that's the most practical, mainly for footprint reasons in the parking lot. The parking lot is very crowded, and BART is very sensitive about us taking too many parking spaces. So we had to go with something kind of small rather than a mobile refueler, which was our first idea. And then we'll have some little neighborhood EVs parked there. So hopefully you'll be hearing about this one. I'll say a few words about the Pacific Region Combined Heat and Power Application Center. This is a Department of Energy and California Energy Commission sponsored center. Some of my CEC colleagues are here, actually, who are helping us manage this. The center is run by UC Berkeley, UC Irvine, and San Diego State University, all working in partnership to promote combined heat and power as an energy efficiency alternative for California. And right now, there are about 7 gigawatts of combined heat and power in California. It's about 17% of California's capacity. So California, combined heat and power is very important for California now. Unfortunately, a lot of those projects are expiring that were started in the 80s. The licenses with the utilities to operate those are expiring, and some of them are having difficulty getting renewed. So we're actually at risk of having some of those projects go away right at a time when we need more capacity. And there have been studies that show that the remaining CHP capacity in California is really quite large. So we're working on trying to access that. We do have an event coming up that's focused on biofuels and bioenergy and combined heat and power in Napa Valley in April. So I'm going to leave some of these around if you're interested in this idea of bioenergy and farm food processing energy. It certainly does have some air quality implications as well, and this has a strong regulatory focus, so may be of interest to ARB. And there's the website for that. I think I'm going to skip these 2 in the interest of time. A couple other projects we're doing at Berkeley, but you have slides if you're interested in these. Let's get on with the main event here. So, hydrogen energy stations. What are these all about? Well, the idea here is that when we start thinking about hydrogen infrastructure, it's rather a difficult problem because you're talking about a new fuel that's not currently available. It's very different than battery electric cars or plug-in hybrids where we have wall plugs everywhere. Hydrogen is not dispensed. It's widely used in industry. In fact, globally, about 50 million tons of hydrogen are used every year. So it's not a new thing in an industrial sense. But in terms of dispensing it to consumers, that is a new thing. And so the problem is that you can envision a future with lots of hydrogen cars and economic hydrogen if you had pipelines to distribute it everywhere, large production plants and pipelines. I mean, that could be the end state. But how do you get there? How do you get to a future where you have lots of hydrogen cars and lots of hydrogen stations and pipelines and so forth? You can't just jump right to that because the startup costs of that are huge. So it's a bit of an overused cliche at this point, this chicken or the egg problem, but it's apt, I think. And so the problem is that people aren't going to buy hydrogen cars until there are places to refuel them, but no one really wants to build a bunch of hydrogen stations until there's enough cars to make some sort of business out of that. And so it's kind of a conundrum. And it's because the economics of hydrogen production and distribution are very challenging for small numbers of vehicles to be refueled. It's just there's some costs that don't really scale that well, and so small stations are relatively expensive. So what is the hydrogen energy station idea? The basic idea is co-production of electricity and hydrogen at the same location. The idea there being that you can produce electricity today and use it today, and you can have hydrogen capacity available, and maybe you use it a little bit with these early vehicles, but the hydrogen production and dispensing part can be sort of an offshoot of this larger scheme that mainly initially would be to produce electricity, or at least significantly to produce electricity. You can have stations that would be based on reformer technology, where you'd have natural gas being reformed into hydrogen, which then goes into stationary fuel cells to produce electricity, or it could be another technology. And then some of that hydrogen would then be purified for vehicles. There's a lot of different designs for these things, and it's something I kind of started studying and was very naive about how complicated this could be in terms of the types of technologies involved, types of settings, all the different complexities, and we'll go through some of those, and I think you'll get a sense of it. And so you can think of stations that would mainly be for electricity production, where you'd be, supplying power to a building, a large building, or potentially selling it to the grid if you believe you can do that, or if you can convince the utility to let you do that. Or you could mainly have hydrogen production with a small amount of electricity, or it could be variable, where you start with mostly electricity, a little bit of hydrogen, but then you try to scale the hydrogen side up as you get more vehicles coming along. Lots of input data and assumptions required, which we'll show you in a minute. Just want to show this really quickly, that when you think about greenhouse gases from hydrogen infrastructure, this blue line would be a typical small reformer station, and the greenhouse gas emissions from that. And you can see, depending on the a little trouble with the pointer here. There we go. Depending on the efficiency of the vehicle, the emissions associated with producing hydrogen from natural gas for vehicles can be comparable to hybrid vehicles, or perhaps a little bit better than conventional vehicles. So the important point is that even if you are producing hydrogen from a fossil fuel, from natural gas, it's certainly not a step backward, and it's probably at least a small step forward. Some slightly newer studies show a 20 to 40% reduction in greenhouse gases from hydrogen-powered vehicles using natural gas produced hydrogen. And you'll see that the black line below that is a reformer energy station. So similar technology, but now it's also co-producing electricity. And at least this analysis showed that you get somewhat lower greenhouse gases through this energy station concept than you would from the others. Of course, where we really want to be is on one of those green or red lines, where you're either using landfill gas and cleaning that up, which is technically challenging, but interesting, or using electrolyzer and wind power, solar power, where you can basically eliminate greenhouse gases from the transportation sector. I mean, that's the holy grail, right? But it's expensive today. So I was interested. I was about, pretty far along through this analysis a few years ago when the executive order for the hydrogen highway network came out. And I was somewhat amused to see this statement where it says, whereas the economic feasibility of a hydrogen infrastructure is enhanced by building hydrogen energy stations that power vehicles as well as supply electricity for California's power needs. And I started thinking about this, and I was like, is that true? Because I was trying to convince myself that that's true, and I wasn't able to do it yet. But I would submit, and this is kind of the crux of the argument today, there's two ways to read this, I think. One way to read it is that hydrogen energy stations make hydrogen infrastructure economically attractive in the near term. But it doesn't really say that. It says it enhances the economic feasibility. And I think that is an important distinction, in that if you can show that hydrogen energy stations can produce hydrogen for a certain number of vehicles at lower cost than the alternative, which is a dedicated station, then you could say that the economic feasibility is being enhanced, even if they're not profitable. The point I'm trying to make is you're going to lose money either way in the early stages of this game. There's almost no way around that I see. But if energy stations can lower that hurdle, it's an Amory Levin's expression of tunneling through the cost barrier. If energy stations can help you tunnel through that cost barrier and lower the hurdles, you're still losing money, but you might lose less money in order to get to the point where you're making money. And that's kind of my thesis today, is that energy stations are a way of lowering the hurdles, potentially a way of lowering the hurdles to getting to that. So it doesn't necessarily mean they have to be profitable from the get-go, and I don't think they will be. But if it can help to enable that, then maybe there's something here. So why might this be interesting? Well, I've kind of already alluded to this, but when you have small stations with low amounts of throughput of hydrogen, the economics are very challenging. There's risks of stranded assets. If the markets develop more slowly than we expect, those stations are just going to sit there and be stranded, and energy companies are very worried about that. A lot of the stations that have already been built are underutilized. Mobile refuelers are another option for getting initial amounts of infrastructure out there, but they can't work everywhere for reasons we could talk about. And then there's this possibility of sort of cross-subsidizing. If the electricity side of the business can make money, then you can sort of cross-subsidize the hydrogen side. And then finally, by making dual use of the reformer, one thing that's interesting about reformers is that there are some scale effects with reformer costs, where if you make a reformer or you buy a reformer that's twice as big, it doesn't cost twice as much. It might cost 1.5 times as much. So if you can think about an energy station with a hydrogen part using a chunk of the reformer and the electricity side using a chunk of the reformer, there's some potential synergies there. So this is kind of a schematic of how this might look. What you have is the top part, which is the green circle, which is the distributed power generation part of the game, where you're producing hydrogen from a natural gas reformer and putting it into a fuel cell and making electricity, capturing waste heat for the building, and supplementing that with grid power if you need to. That can be a good business model. It's a tricky business model, and it's sort of a marginal one today. With fuel cell-based generation, it can be a good business model with more traditional, cheaper generators. And then here's the hydrogen side down below, where you're pressurizing the hydrogen more, purifying it, pressurizing it, and then dispensing it to vehicles. And that, for less than 30 to 50 vehicles a day, is almost certainly a bad business model today. And you really need to get to more than 50 vehicles a day coming through a station before the economics can start to look good. So if you're thinking about early stages of the game where you have maybe 10 or 15 vehicles a day coming through, this energy station concept might make sense. One of these stations has been built so far. This one, or maybe two, one for demonstration purposes. This is the more enduring one. This one was built in Las Vegas based on a plug power PEM fuel cell unit. It was built several years ago. It was very expensive to build. I'm not sure the exact numbers, but I know they were high. And it's producing hydrogen that I believe is being used for a couple of buses that are being operated in that area. And I know that it's worked, but that there were some technical problems with the fuel cell technology, and I don't know the full story, but I know there were some issues with it technically. But it did demonstrate the concept and show that, yes, this can be done. Here's a Chevron Texaco concept of an energy station of the future. And they're definitely interested in this idea where you would have hydrogen produced for vehicles and then electricity also being produced from the same station. This is, in fact, the new Chevron station at AC Transit in Oakland, which is making hydrogen from natural gas reforming on site. And it's not an energy station yet, but apparently has been designed in such a way that you could add the electricity generation component at a later date. And whether or not they'll actually do that or not, I'm not sure even they know, but it apparently has been sort of pre-wired, if you will, to be an energy station in the future. So now to switch to the economic analysis that I've done of this, I started studying this as a postdoc at UC Berkeley 5 or so years ago. And the initial funding for this came from a proposal that I wrote to the UC Energy Institute. And then we got a little bit of additional money from BP and Daimler Chrysler. I developed a MATLAB-based model to analyze this. And again, got way more complicated than I thought it was going to be at the outset. I kind of bit off more than I could chew, but kept whacking away on it until I finally got something I was happy with. And so I built this a model I call CETEEM, which is a Simulink-based model. It has several hundred Simulink blocks to calculate through the rather complicated economics of these types of stations. And the first stations I looked at were service station locations where you'd have relatively small fuel cells at a gas station type place, and then another type of energy station that would be coupled with an office building where you could think about larger fuel cells and using more power on site and looking at the differences between those two, and also being able to use more of the waste heat at the office building locations. So I did this analysis. The report's available through the UCI website. And then I put it aside for a couple years and did some more work on just looking at hydrogen production and other, sort of hydrogen-related things, but didn't really beat up on the energy station stuff anymore. But then I got interested in it again with some funding that I got through the UC Davis Hydrogen Pathways program to take another cut at this, and have been working on that for the past couple years. Expected to have it done now because I was working with a graduate student named Jonathan Weinert, who some of you know is a very talented graduate student, and started working with me on this. Then he got interested in China and electric bikes and scooters in China. Now he's off in Shanghai doing that, which I'm excited about for him because he's doing some really interesting work. But he kind of left me in the lurch on this energy station stuff. So now I've been having to do it. And so it's been a little bit more slow going than I'd initially expected because I've been just whacking away at it myself. Again, lots of variables and data go into this kind of analysis. On the technical side, you can sort of see there's a bunch of capacities and efficiencies and performance type variables that you need to consider for the fuel cell, the reformers, compressors, all that stuff. Think about, if you're going to think about trying to capture the waste heat from the fuel cell, you have to think about the combined heat and power application. Are you heating hot water? Are you, from PEM fuel cells, that's really about all you can do. But once you get into high temperature fuel cells, you can think about all sorts of other uses for the waste heat. Emission factors, this model does calculate emissions as well. And then the economic side is even more complicated, where you've got capital costs, operation and maintenance costs for all the equipment, cost of fuel, electricity costs. And when you start thinking about commercial sites for these things, commercial sites pay for electricity differently than residential sites do. Our bills tend to just be dollars per kilowatt hour, and they're tiered, but they're fairly simple in that regard. Commercial customers tend to pay for electricity in a couple different ways. They pay an energy charge, which is $1 per kilowatt hour kind of charge, but then they also pay what's called a demand charge, which is based on their peak kilowatt usage of electricity per month. So the highest watermark basically per month on their electricity usage, they pay a demand charge based on that peak usage. So anything they can do to cut that peak can reduce their demand charge. And so when you're calculating the benefits of something like this for a commercial site, you want to consider both energy charge and demand charge savings, not just one or the other. So you have to think about what were the building electrical load profiles before you did this and after to get at what are the demand charge savings. And then if you want to think about being able to sell power back to the utility, you have to think about, well, what would they be willing to pay? What kind of price could you get? If you're a solar customer in California today and you have net metering, you can put power back on the grid for full retail. You're getting credit for the full retail price. But no utility that I know of is going to pay you full retail for power that you're generating from some other source, unless they're mandated to do that. So you'd think that they'd be willing to pay you something for it around what their wholesale power price is. I mean, they should be willing to. But of course, politically, that can be interesting. And then there are all these installation and permitting costs and things like that to consider. So fun stuff. So here's the top level of this CETEEM model. Again, it's a Simulink model, so it has sort of a graphical interface. That's one reason I like it. I've worked with a lot of spreadsheet models, and I get a little tired of looking at seas of numbers. So something that has a little bit of a graphical interface I find a little more fun to work with. And then this thing has lots of nested complexity. So you kind of burrow down into it. There's about 7 layers, I would say. Lots of Simulink blocks. You could click on that economics block in the lower right-hand corner, for example, and get into all the economics calculations, and there's blocks and blocks and blocks. All right. Here's kind of just a real, very stylized version of how it works. You feed all these cost and technical specification data in, building load profiles that vary over a daily cycle and that even have annual variation. I'll show you. And then some sort of vehicle load profile for the hydrogen sales. You could assume that the vehicles are coming steadily, but that's not how vehicles refuel. You tend to get waves of vehicle refueling in the morning and the evening. So you probably want to think about that. And then it produces a lot of outputs, but these are just a few of them. Cost of electricity produced, cost of hydrogen, the total cost of operating a station over a year, and the fuel cell system efficiency that you get by operating it, and the emissions are just some of the outputs. This shows how the fuel cell system is characterized, and I don't have a detailed, complicated fuel cell performance model built into this thing because I don't really need one. Those things exist, and you could nest it in there if you wanted, but from an economics perspective, what you really care about is what is the efficiency of the fuel cell at various power levels. Now, it is important, though, to not just pick a number for fuel cell efficiency and say, fuel cells are about 50% efficient and run with that, because you're going to be missing the boat, because fuel cell efficiency is fairly consistent, across a range, but it does roll off quite a bit, and these are different for different technologies and so forth. But you can see you can get pretty different efficiency operating at full power than you can at part load, where they actually operate more efficiently, but where you're not getting as much power out. Just kind of a trade-off there. And then at very low power levels, you can get it really rolling off because you have parasitic loads that are operating then, and you're not producing much power. So these are some different curves for whether you're operating at high or low pressure, which stationary fuel cells will typically operate at lower pressure. Fuel cells for vehicles will typically operate at higher pressure. And I have these in here for reasons so I can do analysis of vehicle fuel cells as well. And then you can also operate on pure hydrogen or a reformate, which is a stream of hydrogen mixed with other gases. You don't get as good a performance if you're running on reformate. You get better performance with pure hydrogen, but you have to have pure hydrogen. That's sort of how that works. When you're thinking about the electricity loads, this is a service station case now. Kind of interesting about this is that the service station loads actually highest in the evening when the lights are on at the station. So this is very different than an office building load, which typically would peak during the middle of the day. Gas stations have different kinds of loads. But then you have to think about what are the electricity loads once you're also compressing the hydrogen for the vehicles, because that adds electrical load to the station. So you need to account for that. So this just shows one estimate for how those electricity loads would add for the hydrogen compression for vehicles. These are office building loads. This would be kind of a typical medium-sized office building in California. And you can see here, gets really complicated because not only do you have that 24-hour variation, typically gas station loads are pretty consistent throughout the year. They don't really change from summer to winter. On the other hand, office building loads change a lot in California in most places. And you can see how much peakier and higher the summer loads are than loads in the spring. Typically the spring and fall will be the lowest. You'll have very high loads in the summer for air conditioning, and then winter, which would be January, or somewhere sort of in between. So the way I deal with this, and this is really an important dynamic to get to, because you don't really want to assume that the electrical loads of the office building are the same year-round. They're not. And so what I've done is come up with a way, in theory you could have 8,760 hours of data and run that through. The way the model I built works, it runs on a daily basis. So what I do is I select day types to serve as proxies for multiple days throughout the year. So you might imagine that December is kind of like January and February, so you can use January as a proxy for December, January, and February, and maybe that's about where it runs out. So I have 4 different months and then 3 different day types for each month: weekend, weekday, and peak day. And those represent days of the month and certain numbers of days of each month. So you can use 12 different day types to characterize a year reasonably well. So I want to show you now the new analysis cases I've put together just in the last month or two based on data that I've been sifting over for a year or so before that. These are service station designs. So the idea of basing the station at a service station, various fuel cell sizes, or at least a couple different fuel cell sizes. And the key improvements since the first round of analysis that I did a couple years ago are better analysis of reformer and hydrogen storage sizing. And Jonathan Weinert, this is where Jonathan really did help me before he took off to China, and helped to think about how you would size the reformer and hydrogen storage for these stations. There's a trade-off there, because if you have a really big reformer and compressor, you can get away with less storage because the reformer and compressor can keep up better. If you want to get away with a smaller reformer and compressor, you need more storage. And there's a trade-off you have to consider. Reformer costs are pretty high, so today it looks like you'd be better off having more storage and trying to minimize the size of the reformer and compressor, but that's a design trade-off that you need to think about. And then Jonathan put together what he calls a compendium of hydrogen refueling cost estimates called SHREC, and gathered a bunch of data on reformer costs, storage costs, compressor costs, all this stuff. So we have new cost estimates for some of the components, much better than I had a few years ago, which were really based on the literature, and that we're looking out to higher volumes of production than we have today. So they were more optimistic and kind of forward-looking. And then I have some new data on PEM system performance from my friends at United Technologies that I've included. This is kind of how the hydrogen storage system works for an energy station. And what you have is these low bars. This would be, I think this is a station that has a 40 kilowatt fuel cell and refuels 10 vehicles a day. And the bars on either side that you're seeing that are flat are the hydrogen demand for the fuel cell. And then there's additional hydrogen demand in the middle of the day for vehicles, again, that has these 2 peaks in the morning and the evening, a little bit during the middle of the day. And then you have the hydrogen demand, again, just for electricity production in the evening. And this is what the storage system has to do. You need to build up storage at night with the reformer and compressor running and so forth. And then it gets drawn down fairly dramatically during the vehicle refueling events. So you need to size the storage to meet these dual demands of the vehicles and the electricity production. So here's some of the sort of base case assumptions, and there's so many assumptions that go into this. I want to make it really clear. There's a lot of need to do sensitivity analysis for this type of work, and so in the report that I'll produce here in a few months, there will be sensitivity analysis on a lot of these things. But these are the sort of base case assumptions. One thing is that the service station has fairly consistent hydrogen demand, so we know there's 10 vehicles a day coming through every day in that profile. In reality, there'd be more randomness to that, but so that's a little bit idealized. It's a reformer-based system, and again, ultimately we want to get to electrolyzers and wind power and all that, but near term, to make hydrogen economically competitive, you really probably have to think about natural gas reforming as a first step, at least for a lot of the stations. And I assumed a natural gas price of $7 a gigajoule, which is about today's price. When I did this analysis 5 years ago, we were just leaving a regime where natural gas was $3 or $4 a gigajoule. I don't think we're ever going to see those days again, but maybe we will. So that's another good role for sensitivity analysis. I used PG&E electricity costs for commercial customers, again, that have that energy plus demand charge type structure, plus a fixed monthly charge as well. Also assumed, and this is very important, in order for the economics, I assumed that you would be able to use waste heat from the fuel cell to heat hot water nearby. Now, you can't do that at a lot of just gas stations because they have bathrooms and maybe a little mini mart kind of thing, but they don't really have good thermal loads. So I'm assuming for these stations that the gas station is located near somewhere that could use hot water, whether it's a hotel or laundry facility or a restaurant, and it has pretty consistent need for that. By regulation now, you can't just sell power across a public road to your neighbor. That's not allowed. But you can sell hot water. You can run a hot water pipe pretty much wherever you want. So there's reason to think this might be possible, but I want to stress that is an important assumption because in order to get the self-generation incentive program incentive for stationary fuel cells, which is $2.50 a watt right now, which is a very important incentive, you have to have heat recovery to get that. If you don't have heat recovery, you don't get that incentive, and then the economics would look very different here. So I want to emphasize that. I looked at stations with 10 and 50 vehicles refueled per day, and the hydrogen would be sold at about $3 a kilogram, or about the going price of gasoline in energy terms, again, as a base case assumption. I assumed PEM fuel cell capital cost of about $4,000 a kilowatt, which is then $1,500 a kilowatt after the incentive. Now, that's a very uncertain number. I think that's about where PEM fuel cell system costs are today, but again, a good place for sensitivity analysis. And the goal for stationary fuel cells is durability of 40 or 50,000 hours, or about 5 years between major stack replacements. PEM fuel cell durability just isn't there right now, at least as far as I know. So I assume that at that $4,000 a kilowatt level, you could maybe expect about 15,000 hours of durability. Now, this is an area I'm really interested in feedback. If anyone has good data on stationary fuel cell durability, I'd love to see it. But as a base case, I assume that. And of course, you can look at cases where you get 40,000 hours and see what that looks like and so forth. And then other cost analysis and so forth. Alrighty, so this is the first case. 40 kilowatt fuel cell, energy station, 10 vehicles a day refueled, all fuel cell power used on site. The electrical loads for the station never drop below 40 kilowatts at a typical gas station, so you can use all the power on site. The system's operating 24 hours a day to meet those electrical loads. We estimated the need for 34 kilograms of storage. So you end up with about a $500,000 station. Fuel cell efficiency, including the reformer, of around 33%. The annual cost of running the station, I'll show you some summary slides in a minute, so we'll go through these quick. The cost of running the station, the cost, so it's not a profitable venture. The cost of running the station is about $78,000 a year, and cost of hydrogen production a little bit more than what you're selling it for. Of course, you could sell it for more if you believe you could do that. Second case, 80 kilowatt fuel cell now, so kind of oversized for the station application, still using all the fuel cell power on site, but you're load following now. So you're not running at 80 kilowatts all the time. You're meeting the loads of the station, which vary from about 40 to 80. So it's sort of a load following thing. Again, operating around the clock, a little more storage needed, a little bit more expensive station, and a little bit less expensive to operate because you're paying more for the fuel cell capital, but in this case, the fuel cell capital is pretty cheap because you're getting that incentive that helps pay it down. And your efficiency is better. With the larger fuel cell, you're operating at less than peak power, so your efficiency is actually improved a little bit. So it actually looks a little bit better economically on an annual basis. More expensive capital, but a little cheaper to operate, better efficiency. The next case is the same as case number 2, but in this case, you have that 80 kilowatt fuel cell, but instead of load following, you're only operating it up to 40 kilowatts. You're basically operating it at 40 kilowatts. So again, to try to get better efficiency, you're backing off, you're basically derating the fuel cell system and operating it at 40 kilowatts, and you get better efficiency, so there's some sort of trade-offs here where you're paying more for the capital, you're not producing as much power as with the other case, so it's actually a little bit more expensive on an annual basis, but better efficiency. The fourth case, now we're up to a 200 kilowatt fuel cell and 10 vehicles a day refueled. Now you're meeting the local demands, plus you're selling power to the grid at what I'm assuming the excess power that you don't need. You're selling your excess power at 8 cents a kilowatt hour, which is probably a little higher than most utilities would be willing to pay you, but it's sort of between a wholesale and retail rate, which may be reasonable. And you need more storage because you have a larger fuel cell system. The capital cost now, you're getting up close to $1 million for this station, and the annual cost is pretty high, a couple $100,000 per year to operate it. So perhaps not as attractive. Okay, so I was thinking this was the same one. This one is just slightly different. Now, because of the durability of the PEM fuel cell, we're assuming that instead of operating it 24 hours a day, you would only operate it for 6 hours a day when your demands are the highest, so that you're not just running through that durability, over a course of 2 years. With that 15,000 hours, you have to replace the fuel cell stack every 2 years. In this case, you're only operating it for 6 hours a day, so the fuel cell stack lasts 7 years before having to be replaced. So there's an advantage there. But you're not making as intensive use of that capital because you're only using it for 6 hours a day. You're producing less electricity, but you're trying to, kind of use the fuel cell when it's most valuable to shave your peak and to produce power during those peak times. And you get kind of similar results, about $1 million a year station, and then about $100,000 per year cost of running it. So I want to stress these are very near-term cases. I mean, these are pretty much here and now type cases. If you wanted to build one of these in the next few years, this is roughly what we would expect. Now, this is a 200 kilowatt fuel cell, but we go up to 50 vehicles a day. So you add a second dispensing pump to accommodate 50 vehicles, and you're selling power back to the grid at 8 cents a kilowatt hour, similar to the other one. You're now up to about a $1.4 million station, and your cost of operating it is about $167,000 a year. But your cost of hydrogen production is down now because you have a bigger station. The economics of hydrogen production are getting a little better, so you're down to about $2.50 a kilogram for the cost of producing hydrogen. Seventh case is basically, it's the 200 kilowatt plus 50 vehicles. But in this case, I said, what if natural gas prices drop down to $5 a gigajoule? You could get kind of a sweetheart deal for natural gas, and instead of $7 a gigajoule, it's $5. How much does that help you? Well, it helps quite a lot. Drops the annual cost down considerably, and the cost of hydrogen production goes down to just over $2 a kilogram. So if we get back to that regime, this shows you how sensitive the natural gas price assumption this analysis is to natural gas prices. It's an important input variable. So this just shows some summaries of those cases. And here's back to that thesis I had about, well, maybe energy stations aren't going to make a lot of money, but if they can save money compared to the alternative, maybe they're of interest as a near-term sort of transitional strategy. And so over here, I've calculated the costs, and the CETEEM model can also be used to calculate costs of just hydrogen stations or just distributed generation stations, or this sort of hybrid of both. These are costs of, on the right, are costs of just hydrogen stations that would fuel 10 or 50 vehicles a day. And then the case on the left are the case I've just showed you in order 1, 2, 3, 4, 5, 6, 7. And so comparing the first 5 cases, which are 10 vehicle per day refueling operations, to the bar on the right, but the one on the left that says SS010, that line then corresponds to the cost of the 10 vehicle per day hydrogen only station. And you can see that some of the energy station designs have operating costs that are a little bit lower than just the cost of the hydrogen station. So the electricity, the synergies of doing this, the shared reformer cost, the electricity side of the business, and so forth, with the SGIP incentive that's paying down the cost of those fuel cells a lot, let's not forget that, does appear that at least in some cases you could have annual operating costs that are a little bit lower than just the dedicated station. So there's that. Then look at the other bars, the 50 vehicle per day stations, same thing. The cost of operating a station that only produces hydrogen for vehicles, 50 vehicles a day, are higher than those 2 energy station cases where it's coupled with a 200 kilowatt stationary fuel cell. All of these are costing you money. You're not making money here. You're not profitable, but you're losing less money to get this whole thing going than you would just with dedicated stations that are refueling small numbers of vehicles. It highlights how challenging it is to get this hydrogen economy going. It's not going to be easy. These are the same results, but in terms of cost per kilogram of producing the hydrogen, generally similar conclusions. Okay, so I'm going to very quickly, want to throw this up into questions soon, but run through a few of the older analysis cases I did 4 or 5 years ago. I want to stress that these capital cost estimates are from the technical literature. They assume higher production volumes in the future. So they're thinking about, future production scenario, not in the here and now. higher production volumes, much lower capital costs in some cases, no SGIP incentive. So what we assume the cost of fuel cell is, that's what it costs, because we assume that by then the incentives have gone away. Waste heat recovery now for office buildings, but not for the gas stations, because before I didn't assume you could do any heat recovery for the gas stations because you just don't have good thermal loads there. And then the sizing of the storage and the reformers and stuff was a little less careful back then. That's a nice way of saying more crude. And so this is what I came up with then, and the conclusions are broadly similar, that if you look over here, these are the costs of operating hydrogen stations with either 25 or 40 kilowatt fuel cells in these cases, and then 5 to 15 vehicles per day being refueled. So these are a bunch of cases. These are the costs of operating the hydrogen stations per year that are only producing hydrogen for vehicles. These are the costs of the energy stations. Again, lower capital cost assumptions for the future. Some of these, there's medium term, which would be 5 to 10 years out, and then future high and low cases, which are even further out than that. So you can see only in some very optimistic cases with these small numbers of vehicles and small fuel cells can you get actual net profits from doing this. But if you subtract these two, these are the savings here from operating the energy station relative to the hydrogen station. So you lose less money. Isn't that great? And then if you start thinking about stations that would then produce more and more hydrogen for vehicles, and the number of vehicles starts increasing over time, this axis is the number of vehicles per day being refueled. And what you can see is that, and then the lines are different hydrogen sales prices. $10 a gigajoule would be very low. Again, remember I did this when gasoline cost $1.50 a gallon probably or something, which is probably about what that is. If you look at the case, the green line, where you're selling the hydrogen for $20 a gigajoule, you do get to a point, pretty quickly where you can begin to, make a little bit of money doing this with these lower cost stations. But if you really want to meet a return on investment target, which is how a business would think about this, if they're going to put capital out there, they want a 10% return on investment or 15% return. If you want to meet that return on investment target, you have to get out to about 50 vehicles a day being refueled, and then you could actually start to even meet a return on investment target. These are some office building cases where the lines above zero are showing that you would, let's see, which was it? Yeah, the lines above are profitable. So if you're above zero, that's profit. The lines in the red, that's losing money. And so you can see if you have some very optimistic future cases, looking at lower fuel cell costs, you can get to significant profits with office building-based designs where you have larger fuel cells and a better economic situation where you're offsetting more retail electricity purchase. But again, you have to be thinking about much lower fuel cell costs than we have today to get to that. All right, well, the last thing I want to talk about is high temperature fuel cell designs. I've been focusing on PEM fuel cells. I'm going to be looking at phosphoric acid designs. Phosphoric acid fuel cells are a commercial product. I don't think the phosphoric acid are going to look radically different than the PEM, but you can have better durability with the phos acid, although you have lower efficiencies. So there'll be a trade-off there. We'll have to see how those look. What I think is really getting interesting is the molten carbonate-based design. Now, this would be different because instead of having that reformer and then splitting the streams for electricity and hydrogen production, now you're using a molten carbonate fuel cell which has internal reforming. You put the natural gas through the fuel cell stack, the thermal conditions and other conditions inside the fuel cell allow it to dissociate into hydrogen inside the fuel cell. So you don't need an extra additional reformer, an external reformer. And what you do is you run natural gas through the fuel cell. Even when you just operate it normally as a fuel cell, there's going to be some hydrogen left in the anode tail gas because you don't want to starve the fuel cell by having no hydrogen at the very end of the fuel cell stack. So you're going to have additional hydrogen coming out that you can then separate out, purify, and then sell to vehicles. And you can actually increase the amount of hydrogen yield simply by putting more natural gas through the fuel cell than you need for electricity production. You get more hydrogen coming out the back end, and then you could purify and sell more of that as you go. So it's a different scheme. It's going to require me to change my model around a little bit and get some new data. Hopefully my friends at Fuel Cell Energy will help out in that regard. And I think it could look very interesting because these molten carbonate fuel cells are starting to come on pretty strong. Here is a recent installation at the Santa Rita jail from just in the fall. This is a Chevron Energy Solutions project with Fuel Cell Energy. About a $6 million project, but a megawatt fuel cell project. Already had about a megawatt of solar at this jail. So there's now 2 megawatts of distributed generation at this site. It's pretty impressive. They did get some incentive money that helped with the economics. I've calculated, based on what they've said, they expect to save a payback of sort of 13 to 14 years. So it's not a short payback period. It's sort of a break-even type venture, I would say. But it is a hedge against higher natural gas prices in the future. It's a demonstration of this very interesting technology. They can get somewhere around 70% overall thermal efficiency with the use of waste heat recovery. Very interesting stuff. And of course, we're seeing these go in other places. University just installed one. I think it was Cal State Northridge. Is that right? Okay. Cal State Northridge just installed one. The Sierra Nevada Brewery has a megawatt of fuel cells. We were talking about over lunch, where they're taking waste beer grain, spent grain from the beer making process, putting it through anaerobic digesters, getting syngas out, and then piping that back into the fuel cell and displacing their natural gas use by 40 or 50%. They've just got this going with the waste gas component. So it's getting pretty interesting. And so I've had a conversation with a guy who's heading up a new project with Air Products and Fuel Cell Energy. His name's Dan Tyndall with Air Products. And they're into phase 3 of a 4-phase project to develop a molten carbonate fuel cell-based hydrogen energy station, where they would do exactly what I just described. They're in the phase 3, which is the design and build phase now. They're putting the thing together out in Connecticut at the fuel cell energy plant based on their 300 kilowatt building block with a PSA, which is pressure swing adsorption based cleanup system, and purifying the hydrogen, or planning to purify the hydrogen. They're planning to deploy this in California in late 2008 or early 2009 at an undisclosed location at this point. And it'll initially have a capability to produce something like 4 to 7 kilograms per hour of hydrogen, so enough to refuel 1 or 2 vehicles per hour at this station. So keeping a very close eye on that project. So some conclusions from this initial energy station work. First of all, the economics of supporting small numbers of fuel cell vehicles at service stations, even with the energy station concept, are challenging, to say the least. However, the losses associated with supporting small numbers of vehicles early on in the transition can potentially be reduced by deploying energy station designs. The economics of office building-based energy stations appear favorable relative to service station designs, because you can think about larger fuel cells without having to sell power back to the grid, and displacing more retail electricity sales, and also having better combined heat and power opportunities. And then key sensitivities in this type of analysis, I think I've made clear, are many, and include natural gas costs, numbers of vehicles refueled, fuel cell system costs and incentives, and a host of others. So complicated stuff. Hopefully you found it interesting. The next steps that I will be doing here are to rerun some of those office building cases that I showed you with near-term assumptions for fuel cell and other equipment costs, looking at phosphoric acid fuel cell designs, which should be a fairly simple extension of what I've already done, examining some of the emissions results that I've been getting and comparing them to other emissions from reformers and electricity production, lots of sensitivity analysis. And then in the longer term, looking at molten carbonate fuel cell and maybe solid oxide fuel cell designs. We don't have commercial solid oxide fuel cells yet, but they're interesting technology for sure, potentially very high efficiency and low cost. More careful analysis of combined heat and power, because you get into these high temperature fuel cells, you can start thinking about much more interesting combined heat and power applications, including the possibility of using absorption chillers and taking waste heat and making cooling for buildings, which you can do with these high temperatures. You can't do that with low temperature fuel cells. You can with high temperature fuel cells. And then thinking about some additional sites and locations that might be particularly attractive. That's it. That's the show. Thank you very much. Appreciate your attention. So, questions?
Yeah. Well, I guess we'll take questions here from the audience. We have a number here from the website, and welcome all of you on the website. I didn't welcome you earlier, so I'll give these to Dr. Lippman now.
Okay. Yeah, I want to start with one here. Anyone? Joe?
Could you repeat that into the mic? Just stay who you are. Sure. Joe Heinzman, Fuel Cell Energy. You talked quite a bit about the economics, losing less money, and just what was the comparison to, obviously between the energy station or just the pure reformer, but then compared to what?
Right. Yeah, it's always really important. I think everybody could hear that out in webland, hopefully. It's always really important to be clear about what you're comparing what to. Absolutely. So in this case, it was losing less money relative to a station that would fuel as many vehicles, but only be a hydrogen station. So what we're finding is that the cost of stations that would just produce hydrogen for vehicles for small numbers of vehicles, are higher than these energy station costs on an annual basis. So you'd be losing less money compared to that other venture. Any of these are more expensive than running a conventional gas station, which the margins at gas stations are very, very tight these days, although you wouldn't know it by the prices we're paying at the pump. So those are profitable. But if you start thinking about a dedicated hydrogen station, and by dedicated station, I mean, that could still be a component of a gasoline station. It's just, it's going to be a pretty different part of the station. It's not, I don't really see synergies between, the hydrogen part of the gasoline station and the gasoline part. There's really, except to the extent you're taking advantage of the same piece of land, I don't really see any advantages there. So comparing, dedicated hydrogen stations to these energy stations was the comparison. Oh, okay. Maybe I misunderstood. Sorry.
Just to follow on, but when you say you're comparing it to just the cost of gasoline right now.
No, cost of hydrogen, cost of stations that would produce hydrogen just for hydrogen vehicles. So think about two worlds, one where you just forget the energy station concept and you're just building small-scale hydrogen stations. Then the other where you couple that with electricity production. So that's the comparison. Is that clear? Almost. We'll get it.
But you're still losing money, and you're losing money compared to the cost of gasoline right now.
Correct.
Okay.
Correct.
The cost of gasoline without the additional thought of where's the greenhouse gas reduction, the monetization of that,
right. Correct.
Monetization of the less emissions.
Yeah.
None of that has been monetized to show where that loss is.
Right. This is a very good question. So,
or you could really be saying this would be the premium cost for reducing CO2, reducing emissions.
That's something I'll try to include in the report. That basically, if you have those dedicated hydrogen stations, you could calculate what is the cost of hydrogen from those stations. So what would you have to sell hydrogen at to break even or make a profit? And that cost will be higher than the price of gasoline today on an energy basis. Now keep in mind that a fuel cell car can go twice as far, roughly, on a given amount of energy than a conventional car. So you really actually want to think about per mile cost. But, if you're just talking about gasoline, a kilogram of hydrogen versus a gallon of gasoline, those are equivalent on an energy basis. The cost of hydrogen is going to be more expensive than gasoline. I would say even once you monetize those externalities, but that would be an interesting analysis to do. I think some of my colleagues at UC Davis have done some of that, where you say, okay, hydrogen is more expensive, but there's less greenhouse gases, less air pollution, so there's some external benefits there. But I still think it's probably going to be more expensive. If that answered the question. Let's take one from the web here. Oh, these are 4 separate questions. Okay, let me take a quick one. How much will we be paying for energy when the Chinese and Indians are using as much as us? How much will we be able to afford to drive then? I don't know if I'm going to touch that one, but I will say that clearly the demand for energy is going up very dramatically with the growth in China and India. That's too big a question to take on. I know that, China's building coal-fired power plants like crazy because of the economic attractiveness, which, is pretty frightening from a climate perspective. So it may be that, our natural gas and our fuel prices won't go up that much. I don't necessarily think they will. However, gasoline, it is a global market. Oil is a global market. As the demand for oil goes up, and if you believe peak oil, I guess you have David Goodstein here from Caltech. Did he talk about peak oil? Yes. Did he talk about peak oil and all that? I would have liked to have seen that. But anyway, if you buy into the sort of peak oil argument, there certainly are reasons to think that gasoline prices are going to continue to rise. And so the cost of driving gasoline cars could continue to go up, and that can make alternatives like ethanol and hydrogen more attractive. These questions from the web are pretty, let's say they're not pointed at the energy station concept. They're a little bit more general, perhaps for another day. How much transportation fuel use could be avoided by living in villages surrounded by green belts of 10 to 20 miles? How much of the products which are trucked around in semis are really necessities? Do we really need leaf blowers and power mowers? These are pretty broad philosophical questions. Certainly, but they do get to an important point, and something that I always emphasize in a talk on hydrogen is that, making vehicles cleaner and more efficient is only part of the solution, clearly. There are too many cars and too many, needs for automobiles. So, clearly I've been working a lot on the automotive side of the equation, but I have colleagues who are doing more on the land use side, and our Transportation Sustainability Research Center at UC Berkeley has a significant component focused on land use and urban form, how to design cities in ways that people don't need to drive so much, how to link, like the EasyConnect project I showed you, how to link people up to public transit better so they don't need to drive so much, telecommuting, all of those things. I mean, we can make cars cleaner, and we need to make cars cleaner because people are still going to drive, no matter, even if we do all those things, there's still going to be a lot of cars on the road. But in no way do I mean to imply that that's a complete solution. I mean, we really need to get to some of the root causes of our transportation energy woes, not just clean up the vehicle technology, which is really more of a Band-Aid kind of solution in a lot of ways. So I think that does get to a good point. Other questions here? Yeah, Tony?
You mentioned something about Santa Rita jail, the molten carbonate. Does that have a transportation component into that project?
Not directly, no. When they commissioned that project, they did have some of the AC Transit fuel cell buses out there. Mm-hmm. And so, but I think that was just kind of a side thing. So there's no there's no hydrogen fuel production from that. Although I do believe I heard the manager of that project say something about that. So there may be some discussions of fuel cell energy. I don't know if Kelly would want to come on it. There may be some discussion about trying to have some hydrogen production for vehicles out there, maybe as a way to refuel some of those AC Transit buses. But I'm not aware of any transportation connection to that particular project at this point.
Well, are there projects now in I know there was one in Sunline where this concept has been tried, right? Are there projects now on various phases where transportation and an energy station concept?
Right. The three that I'm aware of are the Las Vegas station that I showed you that was based on a plug power fuel cell unit in Nevada. There was a demonstration that Hydrogenics did up in Toronto where they had electricity production, I believe wind-powered hydrogen production, and an electrolyzer, and then they compressed hydrogen for vehicles. That's sort of a temporary demonstration. I don't think that one is still running, but that was a Hydrogenics project up in Toronto.
Yeah.
And then the other one I'm aware of is the molten carbonate project that Fuel Cell Energy and Air Products are doing, that they're building the station now and testing it, and then they're going to ship it out to California towards the end of the year. Those are the only three that I'm aware of that couple electricity production and vehicle fuel, for hydrogen at least. Maybe there's some others.
Has somebody approached us? I'm with Pacific Gas and Electric Company. Has somebody approached us for this? Because with the rollout of SB 76 coming up in the next subsequent years,
right?
Subsequent months or maybe weeks, I know there was some references to this concept in the California Highway implementation, and I know Humboldt was talking about something like this, Humboldt State.
Yeah.
And I think there's some interest in the utility perspective.
I'm glad to hear that.
In collaborating with some folks that are interested,
mm-hmm.
Because it's a fairly novel concept, especially if somehow the grid could be involved when there's excess power or when the power is actually needed.
Right. Yeah, no, I think that's very true. And there is something in the California Hydrogen Highway Station, the RFP, that said something about energy stations, and I can't remember exactly what it said. Maybe Gerhard knows. But basically those stations were required to have a renewable energy component of, I believe, 20% renewables. And if they employed an energy station design, they did not need to meet that renewable component if they maybe had waste heat recovery or something like that.
They had waste heat and also...
Can you repeat that?
Sure, there was an overall energy recovery for the station and also potentially for power production. But I think in that first phase, that initial request proposal, we didn't receive any bids with an energy concept. I mean, they all met the renewable requirement, but no energy concepts.
Yeah, but that's interesting, Tony, that you indicate that PG&E is receptive to this idea because, I showed you some station costs that are pretty high, so I'm not shocked that people aren't, stumbling over themselves to build these energy stations when they could build cheaper stations. But if you do think about a hydrogen station that then has to have a renewable energy component, that adds cost as well. And so maybe an energy station could look relatively attractive compared to these stations that have to have that renewable energy component. You do, I think, though, need to think about the waste heat recovery, and that's not necessarily trivial depending on where the thing is sited. And I'd have to look at those station guidelines to see, but maybe someone will get interested in this, and I'm certainly I'm happy if anyone out there in Webland or wherever is thinking about these energy stations and wants to take advantage of the model I've built to run some economic cases and look at what the economics would look like for purposes of putting together a proposal, I'd be happy to talk with them.
So I'd just like to mention to the group that if anybody's interested to, we're open to discussions. I know Professor Paul Eichmann, what's his name from?
Erickson?
Erickson from Humboldt State.
Oh, no, Peter Lehman?
Peter Lehman, yeah. Peter Lehman came over to PG&E and we try to collaborate on that energy station concept using landfill gas actually, and that was a pretty, we actually entertained the idea. There's going to be a paper presented at the National Hydrogen Conference in San Antonio about that attempt to link up, but we are interested in a concept like that.
That's great. No, Peter's a good friend of mine, and haven't talked with him in a little while, so maybe that's a good reason for me to get in touch with him. I have heard rumors that they're trying to get money to build a hydrogen station up that way, but I don't know anything about it, whether it would include electricity production. They're probably trying to sift through all that now, but I'll touch base with Peter on that. Thanks.
Thanks.
Good people up there at Humboldt. Anyone else?
We have another question from the web. Anybody else here?
It's Aaron Bright from the California Energy Commission. I just kind of wanted to know if you could maybe go over the pricing that you have on there, because I'm kind of curious if you get production prices, and those seem to be a lot lower than what we normally see for hydrogen costs. So is that, production as in just what it's costing to make, or is that the actual cost it would be sold at?
What I assumed was that the sales price would be $20 a gigajoule, because that's about what gasoline sells for. So I just used that as a starting point assumption. Some of the cases had higher production costs than that, and some had lower. But you're right, the production costs are pretty low, and that is because you are taking advantage of, you're only paying for part of the reformer for the hydrogen production. So you're taking advantage of some economies of size there with the reformer. That's why you can get a little bit lower production costs with that. But another reason, I've assumed fairly high reformer efficiencies, I'd say, something like in the low 70%, which I think is considered, on the high end of the range of what you can really get from reformers, although I've heard it's in the 70-ish% range, but I know there's some reformers maybe only doing about 65%. So that may be why my numbers are a little higher than some you've seen, is the reformer efficiency probably a little bit optimistic. And reformer efficiency, when you have high natural gas prices, the reformer efficiency is very important in terms of how much of the natural gas energy throughput you get through to hydrogen. I think that's why. But, we're looking at numbers, $3 to $4 a kilogram kind of production numbers, except for those stations that had the really large 200 kilowatt fuel cell, or not really large, but 200 kilowatt fuel cell with 50 vehicles a day. Then we're starting to see numbers down in the $2 a kilogram, $2.50.
Okay, and the cost to run each station that you had reported in there, that would be based on that number when you're talking about hydrogen revenue, as opposed to, I've been talking to some people, they're saying the hydrogen, that when they sell hydrogen to their companies, chemical companies or whatever, they sell it for about $7 a kilogram. So, that would be, you're talking about the $3 or $5 amounts.
Right. So, definitely, in these kind of cases, the cost of hydrogen to the consumer is essentially being subsidized on some level in order to make it attractive. If we were to calculate sort of a full retail markup, if you hear the cost of the hydrogen production, you also probably want to assume that it's being taxed, because gasoline is taxed. And one issue with hydrogen, maybe as an incentive in the early years, you would let it go through untaxed, but you need to add to the production cost taxes and then profit to get to a retail price that would then be profitable, and then those numbers would be $7 a kilogram or something like that, 6, 7. So that probably squares that, I would think. Okay. So from Weblands, in your case studies involving a stationary PEM fuel cell energy station combined with hydrogen fuel production and dispensing, what is and is not included in the cost estimates? Good question. I tried to be fairly clear about that, but I'm sure I went through it a little too quickly. So what we include are all the capital costs that we know of for the equipment, operation and maintenance costs for the fuel cell and the reformer, fuel costs, and then what I've added in these more recent cases is an estimate of sort of permitting and site preparation costs which seem to be running, sort of $40,000 or $50,000 for a station like this. So we've layered in some costs, but I think permitting and site preparation actually could be quite a bit higher than that for certain sites. We have made some attempt to include some of those squishier kind of permitting and site preparation costs, as well as just the capital costs, operation and maintenance, and fuel costs. But those are the big cost components. And then any electricity you have to buy, that kind of thing. So, I'm interested in, as I put out a draft report, I'll be making that available. If people think that I've missed some cost components that should be in there, this is something we really have been trying to think much more carefully about in the past few years since I did that initial analysis. The initial analysis I showed you that has the longer-term forecast, those were definitely shy on some of these other cost components. I kind of wanted to take a quick look at it, or an initial look at it based on, kind of skeletal costs, if you will. And if that doesn't look good, there's not really much point in layering in a whole bunch more costs because it's definitely not going to make it look any better. So I kind of wanted to take a kind of a long-term view. If these stations become more commonplace in the future and permitting becomes more streamlined and the costs of that become more reasonable, that's what I looked at first. And then these more recent cases included, somewhat higher costs for things like permitting and site preparation and stuff like that. So I tried to include all the costs I could think of that would be real. Okay, maybe we'll do one more. Okay, last question. What are the expected emissions from production of hydrogen? Not only the chemicals involved, i.e. CO2, but the amount emitted, tons per day, especially high-temp molten carbonate fuel cell and solid oxide fuel cell designs. Are there potential wastes associated with production? Well, I'll take a stab at this. Certainly, the natural gas reformers are pretty low emission. For example, the phosphoric acid fuel cell units that were sort of the first large-scale commercial fuel cell units were exempt, I believe, from air permitting requirements even in Los Angeles. So there are emissions from reformers, but they're pretty low. And so, they're something that needs to be studied, and they're of concern, but they're not major sources of emissions. Now, CO2 emissions, definitely the carbon, if you're starting with natural gas, the carbon has to go somewhere. So there are significant CO2 emissions associated with reformers and any natural gas-fired fuel cell. So that, again, speaks to the need to ultimately get towards, you could think about landfill gas or municipal solid waste as sources for hydrogen for fuel cells, but it does speak to the need, if you really care about deep cuts in carbon emissions like Al Gore does, and like most of us, I think, do, then you do need to think about non-fossil fuel-based feedstocks for hydrogen production. The problem is that electrolyzers, if you think reformers are expensive, electrolyzers are more expensive, and wind power has gotten pretty economically competitive, but solar power is still pretty expensive. So anytime you think about renewable hydrogen, that's the end game. And privately, I believe that unless we really strive to get towards that renewable hydrogen future, the whole enterprise is probably not worth pursuing. If the best end state we could think of was a natural gas hydrogen pathway future, I don't think all this effort and cost and complexity is probably worth it to get that kind of incremental benefit. We could probably get that with better hybrid cars, plug-in hybrids or whatever. So we really need to be thinking about a long-term strategy towards really clean, low-carbon hydrogen. But you can't start there. I think it was Steve Ellis from Honda had a good example, a thing he likes to say, which is that expecting the hydrogen economy to start with zero carbon hydrogen is like expecting a newborn baby to get out of the hospital and walk home. You got to start somewhere. You got to walk before you can run. And so I think about it as a transition strategy where you have to get it started with natural gas, at least in a significant measure, to bring down the costs of fuel cells, bring down the cost of the fuel cell vehicles, and then we can start moving towards increasingly clean ways of getting hydrogen. But we can't lose sight of that vision and that goal, or else the whole thing could get kind of off on the wrong track. And that's something I worry about, and that's something I lay awake at night concerned with. So there's a kind of a school of thought on this called technological lock-in or path dependence, where sometimes once you get into a technological regime, it can be hard to transition and to kind of break out of it. You kind of get channeled, and there's a lock-in type of effect. And I get worried that we might get kind of locked into a natural gas hydrogen world and would have a hard time breaking out of that. And so that's why I like the idea that the hydrogen station guidelines include that renewable component. I think some renewable component from the get-go is appropriate so that is always on the table and always part of the picture. But to expect the stations to be 100% renewable, I think is unrealistic from the beginning, and I think it's sort of appropriately designed. Well, thank you very much. I really appreciate you guys coming. Thanks so much to Jerry and to Peter and everyone for organizing this. It's always a pleasure to come up to the Resources Board, and I look forward to working with you guys in the future.
Okay, thank you, Dr. Lippman, and thank all of you. And thank Annalisa Bevins for working this out even though she couldn't come, and Peter Matthews for doing all the background stuff. Thank you.